In this second video, we're going to finish off our computation of the F statistic. We're going to review all the computations using an analysis of variance table, and the very last thing we'll do in this video is begin to look at how we report the results. Let's dig in. In our first video, we saw the experimental situation in which a teacher praised students for their effort in preparing for one test and then recorded their scores on a second test. And we went through the computations to find the sum of squared deviations from the means between the groups, which is the variability due to that praise treatment group. And we also found the sum of squared deviations from the group, from within the group means, and that's the variability that was due to all the random factors besides praise that could be affecting the students. In the previous video, we were sneaking up on the idea of our F statistic as a ratio of these two components, the systematic component on the top and the random component on the bottom. And in this video, we'll figure out how to actually compute that statistic. In the first video, I mentioned that we would be averaging our sums of squares across something that measured sample size and the number of groups. And just as it was when we were looking at our t-tests, that's going to be degrees of freedom. So let's look at how we compute degrees of freedom in this analysis of variance situation. The degrees of freedom represent, at the greatest level, something about the number of subjects, which in this situation was 18. But unlike our t-test, we have to divide those degrees of freedom, some of them to represent the number of groups, and then others of them to represent the number of people. We computed one grand mean and had one large sample, and so that means that our overall degrees of freedom will be n minus 1 for that grand mean that we computed, and in this case that means it's 17. The degrees of freedom that go with the idea of having more than two treatments means that we'll be adjusting our sums of squares so that we've averaged them across something that measures the number of treatments. We use the letter K to stand for the number of groups, and the degrees of freedom between groups, that's the systematic part, the one that's due to the treatment, is going to be K minus 1. In this situation with three groups, 3 minus 1 will be 2. And just as we saw before, if we know the total and we know one component, we're able to get the other by subtraction. So our degrees of freedom within, we could compute directly as n, the total number, minus k, in this case 18 minus 13, or we could, or minus 3 to give us 15, or we could notice that 15 plus 2, when they add up, give us 17, so we could have arrived at the same number of degrees of freedom, 15, if we had done it by subtraction. In analysis of variance, we compute something called the mean square, mean referring to averaging, and in this situation we take the sum of squares between the systematic variability and divide it by the degrees of freedom between, which measures the number of groups. So this is where we're doing what I called averaging earlier in this video. We're averaging the variability between the groups over this degrees of freedom measure that is relative to the size of the groups, the number of groups that we have. We do the same thing with the variability within, that's the random component, and we average the sum of squares, the deviations, within the groups, that's due to all of the individual differences, over the measure that is most to do with the number of individuals that we have in the sample. So once we've computed these mean squares, we are finally ready to compute our F statistic. Our initial logic said that if the variability between groups was large, the systematic part due to the treatment, relative to the variability within group, which is the part that's random, then we would reject the null hypothesis. So these mean squares allow us to compute a ratio of the variability that's systematic in the numerator and then the variability that's random in the denominator. So let's carry out the actual calculations for our example situation. The between squares mean square, we had sum of squares 47.45 between the groups, that systematic component due to the praise, and we had 2 degrees of freedom. When we do the division, we get 23.75 as the mean square. When we look at the random variability, the part that's due to all the individual factors, the sum of the squares, which we computed quite early on, 32.83, the degrees of freedom, 15. When we carry out the division, we find that we've got a much smaller mean square here, 2.189. When I put these two numbers into my equation for the F statistic, 23 divided by 2.189 gives me quite a large F, 10.849. Remember, when the null hypothesis is true, we expect F to be about 1.00 and to go up in size as the p-value decreases and the probability of significance is going up. So our F of 10.849 is on a track to be statistically significant. We have 2 ways of carrying out our hypothesis test, and they always yield the same result. If I'm looking at a table of critical values, the way the textbook provides for us, then I need to find the critical value from the table, and when the F statistic is greater than that critical value, I'm going to reject the null hypothesis. And you might remember the F curve has a sort of a skewed shape, and that critical value that I'm finding in the table, so I'm going to just put CV for critical value, is cutting off 5% if I'm at the 0.05 level of the area in the tail of the curve. So if the value that I actually compute turns out to be even greater than the critical value, if it came out, say, about here, you can see that I'm in the rejection region, and in fact, the p-value, which our statistical software will compute for it, the p-value is saying what's the area of the curve beyond my actual value of F, the one that I calculated. So whenever my calculated F is above a critical value, the p-value, the part of the curve that's beyond my calculated F, will always be less than 0.05. When I have the statistical software doing the calculations, I can just look at the p-value. I don't even need a table, and whenever the p-value is less than alpha, I'll be able to reject the null hypothesis. Note that the critical values of F vary according to both types of degrees of freedom. So we need to look up for the degrees of freedom in the numerator and in the denominator, and then find the value for our particular alpha, whether it's 0.05 or 0.01. I used the software to compute our p-values for our experimental problem, so we already had our F statistic of 10.849. When I used the data analysis tool pack in Excel, and I also carried it out in Google Sheets and got the same result, the software gave me the 10.849 just as I'd computed before. It showed me the same degrees of freedom, 2 and 15, and gave me a p-value, p equals 0.0012. So this is letting me know that in my skewed F curve, if I have 2 and 15 degrees of freedom. When I go down to the point where 10.84 would show up, the area in this little tail beyond 10.84, this area is 0.0012. My alpha area on the other side would be 0.05. So the fact that my p-value is much less than 0.05 lets me know that I should be rejecting the null hypothesis, which is the decision I'm going to make in this test. We've taken quite a long time to go through these calculations, and you might be wondering, how in heaven's name am I ever going to remember all of these parts? Luckily, long since, the statistical community came up with what it calls an ANOVA table. And on the one hand, it's a great tool for displaying results, but even more than displaying results, it's an excellent tool for calculating them. It lines up the components in a particular order. We tend to compute our degrees of freedom, or our sums of squares, first, and it lines them up so that the between that will be in the numerator and the within that will be in the denominator are first and second, with total at the bottom. So if I've computed my total, whenever I compute either of the others, within or between, I can go ahead and compute the other by subtraction. So this table adds up, going down, for the sums of squares, and the same is true for the degrees of freedom. I have the degrees of freedom related to the number of groups minus 1. Then I have the total number of people minus the number of groups, and finally n minus 1 for my total degrees of freedom. Once I've got the components in that add up to totals, I can use the same table, but now moving across to do my next computations. I need to compute my mean squares, which take a particular sum of squares, divide by its particular degrees of freedom, and I get the mean square. So I can do that for between groups, and I can do it for the random variability within groups, and I have my 2 mean squares. And finally, those 2 components are in exactly the right order to put a dividing line between them and calculate the ratio, 23.7 divided by 2.189, and I get my F statistic. So the table reminds you of the relationships, lets you carry them out, and also displays the results. I've put both a link and a video about the ANOVA table quizzer into our materials for this week. The quizzer basically gives you an analysis of variance table with some of the parts missing from it, and so you would have to figure out how you could fill in the blanks. In this one, which is one of the more difficult ones, I immediately see that I've got 7 degrees of freedom between and 167 within, so I can pretty easily figure out that this must be 160. It's a little harder to figure out some of the other components. For instance, this F statistic of 24 is some unknown mean square divided by 127 gives me 24. If I multiply 24 times 127, it will give me that result. The ANOVA table quizzer basically works like a Sudoku and helps you learn the relationships by remembering which ones add up, which ones divide across, and get used to working with them. I encourage you very strongly to work with the ANOVA table. It's not just that it's fun and a game. If you do it long enough, all of these relationships just become second nature, and you will not have to remember all the equations. You'll just remember what to do. So this slide just gives you a brief review of our ANOVA test so far. We defined our hypotheses, and we set a significance level of alpha in steps 1 and 2. Then we went about the business of computing the F ratio, and all of these steps that we took to get our F statistic are basically step 3 of this particular inferential test. And then finally, step 4 is making a decision to reject or retain the null hypothesis. Just as we saw with t-tests, when we reject the null hypothesis, there will be some follow-up tasks that we need to do. One of them will be computing the effect size, and we will see those in a later piece of information. Also, just like the t-test, we do need to know how to write up our results using APA format. And I've begun the write-up here. It's already looking quite long, but because we have not yet dealt with effect size and a couple of other things, this is not a complete write-up, but the parts that are here are all good. So you may remember our sandwich format. The first part is a narrative English description of what the research question was and a little bit about how the research was carried out. I probably could add a little bit into this sentence to let the reader know early on that there were only 18 students in the class, although the reader could figure that out from the degrees of freedom that are in the actual results later on. After I've asked the question and said a bit about the research, I do the descriptive statistics. In this situation, I'm comparing the 3 means, or at least reporting them, and doing them not so much in terms of the language of statistics, but in terms of the language of the actual variable. So I refer to them as the group that received the most praise or that received moderate praise, rather than calling them Group A or Group B. I want my reader to stay tuned in to what the actual question we studied was. Finally, after all that work, my actual statistical test results show up really quite briefly. The word significant is the only thing that reveals that I rejected my null hypothesis in an explicit way. I have to say which statistic I used, in this case an F. I show the degrees of freedom that go with that statistic and the actual value that I calculated. If I were using the tables in the back of the book, all I could say when I rejected the null hypothesis would be that P was less than 0.05 or 0.01, or I could use interpolation to try to find another number. When I use those data analysis tool packs for either the Mac or for the PC, I get the actual exact p-value, and this is always worth reporting. It lets the reader decide if they wanted to apply a more strict standard than, say, the 0.05 I had selected. If I've reported my p-value, they would be able to make their own decision about rejecting or supporting the null hypothesis. After those results, I will be having to put in a part about effect size, and we will be learning about post hoc tests. Our textbook tells us about the Tukey and the Chaffee tests, and this is where I would put those results if I had a significant test. When I do not have a significant test, there is no effect, so I don't have to talk about effect size, and because I have no effect, I don't have to follow up with post hoc tests to see which pairs actually differed significantly. So after I've put in the quantitative part, I do always close with some piece of narrative so that my non-statistical reader does know what I found out. In this case, I would write that these results are similar to those that were predicted by Dweck's previous research, because I'd mentioned her research in the early part. So that sums up the logic and the computation that go into carrying out our analysis of variance test and computing the F statistic, and shows you the beginning of how to report the results. Analysis of variance, as you can tell, is more complicated than our t-tests were, but with quite a bit of practice and with effort, it does fall into place. One of the quickest ways of getting the components to make sense is with that ANOVA table quizzer, And the second best way is also to start thinking about how you would report the results of various tests that you've read about. Bye-bye. The remaining steps, the effect size and the post hoc tests, are a little bit more complicated and will take a little bit of extra work before you're confident in using them. With practice, however, they too come into play.